Hello everyone, I am Yifeng Teng from Google Research. Today I'm going to talk about description complexity of regular distributions. This is joint work with my colleagues Renato, Balu, and Pratik. The main objective to study in this work is Meyerson's regular distributions. It is one of the most common class of distributions to study in the field of economics and computation. There are multiple equivalent ways to define the regular distributions. One of the definitions is to define the virtual value function v minus 1 minus the CDF over the PDF. The regular distribution is the class of distribution with virtual value function being monotone non-decreasing. Another equivalent definition is to define the revenue curve in the quantile space. The quantile at any price P is defined by 1 minus FP. It is the probability of sale when we set a price P and when the buyer's value drawn from some distribution F. One example is the exponential distribution. For an exponential distribution, the revenue curve is defined by minus Q times log Q in the quantile space. And this is a concave function, so the exponential distributions are regular. Why are regular distributions important? One important aspect is that Meyerson uses to characterize the optimal mechanism for selling multiple bidders a single item. Meyerson's characterization shows that for any allocation, the expected revenue equals to the expected virtual surplus. So this means that when each bidder has independent regular value distribution, a second price auction with monopoly reserve price is a virtual surplus maximizer, thus it is revenue optimal. For irregular distributions, more complicated ironing processes are needed. There are many common distributions that are regular in the study of economics and computation, such as uniform distribution, Gaussian distribution, exponential distribution, and so on. There are also lots of other nice results relying on such a distribution assumption. For example, for the seminal Bulow-Clamper result, where there are multiple IID bidders with regular distribution, they show that the optimal revenue is upper bounded by the second price auction with no reserve, but with one expert bidder recruited with the same distribution. So we know that regular distributions are absolutely more structured than the general distributions. So our question to ask here is that how much more structured are regular distributions? Can we actually quantify this? The way we quantify the structure is by description complexity. This is the term borrowed from theoretical computer science that shows that how many bits do we need to describe something. So absolutely, for the entire class of regular distributions, there are infinitely number of them, so we cannot describe a distribution exactly. Our question to ask here is that how can we do it approximately? What do we mean by approximating a regular distribution? For any distribution, we say that we describe a distribution approximately if we find another distribution such that the two distributions have some small statistical distance. And the distance metric we consider in our study is the Levy distance. So for the Levy distance, we allow the value to perturb by epsilon, and we also allow the cumulative density to perturb by epsilon. Why do we use Levy distance? Because there are previous studies on auction theory saying that if we know the value distributions within small Levy distance, it is good enough for designing near optimal auctions, even in some multi-item, multi-buyer cases. when we are starting the general distribution, we ask how many bits do we need to describe any distribution on 0, 1 within epsilon level distance. So firstly, we observe that O tilde of 1 over epsilon bits are sufficient. Here, O tilde of 1 over epsilon means O 1 over epsilon ignoring the polylog factor. Because we only need to know the CDF function with additive epsilon error for every multiple of epsilon. And it is enough for describing f within epsilon level distance because we allow an error of epsilon in the values. And we can also show that omega 1 over epsilon bits are necessary because at least 1 bit of information is needed to specify the CDF at every multiple of epsilon within additive error of epsilon. So we know that the description complexity bound for general distribution is theta tilde of 1 over epsilon. And in this work, we characterize the description complexity for regular distributions. Our main result is that 1 over square root epsilon bits are necessary and sufficient to describe any regular distribution on 0, 1 within epsilon level distance, ignoring the polylog 1 over epsilon factor. And this result, we can view it as two parts. One part is the description complexity lower bound, and one part is the upper bound. For the lower bound, we prove that there exists a set of regular distributions on 0, 1 with size 2 to the 1 over square root epsilon, such that for any two distributions in this set, their distance is at least epsilon. In the second theorem, we prove the upper bound by saying that for any regular distribution, given oracle access to the CDF function and the PDF function, 1 over square root epsilon queries to the oracles are sufficient to learn f within epsilon level distance. Let's start with the proof of the lower bound. Recall that in the definition of regular distributions, we define the virtual value function and says that the regular distribution is the class of virtual distribution with virtual value function being non-decreasing. And if the PDF is non-decreasing, then we can actually show that the distribution is having monotone hazard rate, and it is also regular. We're going to prove a stronger version of this theorem, saying that even if we replace the class of regular distributions by the class of distributions with non-decreasing PDF, this set, we can still construct such a set of regular distributions with pairwise large statistical distance. The set of distributions are constructed as follows. The distributions are parameterized by a vector B of length n, containing all 0, 1 bits. And here n is 1 over 4 times square root epsilon is of the order of 1 over square root epsilon. We define the base PDF function parameterized by 0 vector to be fb equals to 2 times b, and it is a linear function. And for each bit bk, if bk is switched to 1, we let the PDF function within an interval of length 2 times square root epsilon around some point for k plus 2 times square root epsilon to be set to the same value. So this means that before perturbation, the PDF is linearly increasing around those points, and after perturbation, the distribution becomes uniform around those points defined by those bits equals to 1. And by observing, that the difference between the the CF of two distribution is actually the area difference between below the PDF functions. And after the perturbation, we can show that the CDF actually changes by epsilon as the area below the PDF function changes by square root epsilon in an interval of length square root epsilon. And using this, we have constructed a set of distributions parameterized by this a bit vector of length square root epsilon, and such that for any two bit vectors, their corresponding distribution has a level distance omega epsilon. This proves the lower bound for the description complexity. And now we go to the upper bound proof. For the upper bound proof, we first need to ask the following question. What do we mean by learning f within epsilon level distance? Our observation is that if we can find a sequence of points such that for two neighboring points, either their distance is small within epsilon, or we can characterize the PDF function between the 2 points such that the distance of the 2 points times the PDF range between 2 points is O of epsilon, then from the CF of these points, we can reconstruct a distribution that is epsilon close to the original distribution. The first case corresponds to the definition of level distance where we allow a epsilon error in value. And the second condition is that if the condition is true, then we can actually perturb the PDF function within each small interval. And if we partition the entire interval into multiple small intervals, and within each smaller interval, we know that the PDF change is within the blue rectangle. And the blue rectangles has area at most epsilon, then the CDF difference between the area under the PDF curve before and after perturbation can only be epsilon. So this means that we can have a reconstruct the CDF with epsilon level distance from the original distribution. So our upper bound proof reduced to find such a sequence satisfying those properties, and we want the blue area delta x times delta f to be at most epsilon. If we approximate delta f to be the derivative of f times delta x, then we actually want to discretize the 0-1 interval such that those delta x are at most square root of f prime x over epsilon. And because we know that f is monotone increasing, we can identify ranges where the f prime of x varies within a constant factor and discretize it accordingly. And this can be done via binary search. So we can also show that this binary search only needs 1 square root epsilon breakpoints. But we know that regular or MHR distributions do not have monotone PDFs, as in the previous page. Then what do we do? We actually prove the following lemma, saying that the PDF of regular distribution is almost monotone. That for any regular distribution, if the quantile 1 minus fxi prime and 1 minus fxi are close to each other within a factor of 2, then fx cannot decrease by a factor of 2 for more than a constant number of times in this interval. The implication is that the PDF of the distribution is monotone up to a constant factor if we assume the quantile is within a constant factor. And we can use this lemma to produce a branching procedure for adaptive discretization. So this is almost the same where the PDF is monotone, but here we allow the PDF to decrease slightly. And we are still able to show that we can find those Worah square root epsilon points such that the blue rectangles have area of epsilon. One corollary of our description complexity result is on the pricing query complexity of learning entire regular distributions. The pricing query or threshold query of a distribution is defined by saying that we propose a price query P and we obtain a value sample V drawn from D, but not directly observing its value. We only observe a binary signal whether V is greater than P or not. The pricing query complexity of learning a distribution is to ask the following question: that's how many pricing queries are needed for learning a distribution within epsilon level distance? For the general distributions, the exact pricing query complexity is theta tilde of 1 over epsilon cube. And in this work, we show that the pricing query complexity for learning a regular distribution is actually theta tilde of 1 over epsilon to 2.5. So the gap from this 1 over epsilon to 0.5 description complexity bound is by a Chernoff bound, saying that we actually need 1 over epsilon square queries to a fixed price P to get a good estimation of the CDF of the distribution. And all of the previous results for the PDF and CDF, we only need to approximate the PDF and CDF, and the PDF approximation can be done via a discrete version of the derivative of the CDF function. Another interesting observation is that if we consider pricing query complexity for learning the mixture of two regular distributions, this is actually not a 1 over epsilon square gap from the description complexity. We actually need 1 over epsilon cube pricing queries to learn a mixture of two regular distributions, because similar to some previous work, the mixture of two regular distributions is actually having many properties of irregularity. To summarize the talk, we provide a tight description complexity for approximating a bounded regular distribution on 0, 1 within epsilon level distance. And as a corollary, we also settle the tight pricing query complexity for approximating a bounded regular distribution. And we prove the results via some new observations of regular distributions. That's all. Thank you for listening.